All right, good morning. It is a little bit lonely here. The video will be recorded for your online course at home during this outbreak. Let's continue. Last lecture, we set up these examples. This would be the last example of chapter 10. The example is a flow in a pipe with heating or cooling. Let's say if the flow in of the water has high temperature, when it passes through the pipe, there will be the heat generated or heat released from liquid to the ambient air outside. And we discussed last lecture that in this particular examples, there are momentum transport as well as energy transport. And if we analyze the momentum flux or analyze how velocity would be a function of variable r, zeta, and z, we end up with shell that looks like this. This is the shell that has a full length in z direction because velocity z is not function of z. Velocity z is function of r only. And for the energy, on the other hand, now we see that temperature will be a function of z as well as a function of r. Therefore, the shell for energy balance is supposed to look a little bit different than shell for momentum balance. This is the first example that this kind of behavior occurs. Okay, so the next question would be how to start an equation. Once again, we have momentum transport as well as energy transport. If we start with momentum transport, we have to assume that temperature changes does not affect physical properties such as density and viscosity. On the other hand, if you want to start with temperature or energy balance, you have to assume that the convective transport does not affect that much. If you consider the problems, in this case, we have heating at the wall or cooling at the wall, and the temperature or heat would have in R direction by means of conduction. On the other hand, in Z direction, there will be the convective transport. And this convective transport is really important. If you learn from unit operation 3, you learn that convective transport is more important than conduction. So in this case, definitely we cannot ignore the convective transport. In that sense, it means that we need to know velocity profile first. So keeping that in mind, it means that we have to conduct the calculation based on momentum transport first. So based on this shell of the momentum transport, you set up the flux. If you start again, we have VR, V zeta, Vz. And there's no VR in this case, there's no V zeta in this case, only Vz. And Vz will be a function of R only. There's no function of zeta because the system is symmetry. And if you assume that there's no acceleration within the pipe, the Vc would no longer a function of z. And having Vz as a function of R, so that means we end up with fluxes of Rz, zeta z, zz, right? And here it looks like this. This would be your flux Rz going from the center of the pipe toward the outer rim of the pipe, and that would be flux Vcz going in on this circumference, on this ring, annular ring of the shell, and going out at the bottom. Okay? This is exactly as what we have done in chapter 2. And if you set up the momentum balance like so, assuming density is viscosity is not function of temperature, in that sense, it means that you do the calculation as if the system is isothermal, then you end up with velocity profile Vz equal to V maximum times 1 minus R over capital R squared. Exactly the same thing as we did earlier in chapter 2. So once all the calculation based on momentum is done, we can move on to energy balance. For energy balance, this is the shell for energy balance. If we look for the flux, there will be two main fluxes. First would be QR. QR would go from center outside, this is QR. It's a heat converting or transporting in R direction. Of course, it's go from any R component. These would be QR. Also, if you have warm water or hot water coming in, and once the water passes through the pipe, there will be energy transport out of the pipe that makes the temperature of water lower. So at the end of the pipe, temperature is supposed to be cooler than energy coming in. So you can see the difference in temperature here. Therefore, there will be at least there will be conduction in Z direction as well. At the same time, you see there's a flow of liquid in Z direction together with the difference in temperature in that direction. So it means that we have convection for sure. So we do not know at the moment whether the net flux would go up or going down. So we will follow what we have done so many times, set up the flux along with the direction of the axis. So we have Z-axis going down. In this case, let me use a blue color. So this would be our QZ. This is our QZ. Going in, going out. All right? So setting up shell energy balance. If we look in each direction, let's look at the red direction first, the R direction. So that means I'm looking at shell side. The input term is supposed to be related to QR, or at least combined flux ER. This is combined flux in R direction. The combined flux should enter the shell at location R. So the subscript here is supposed to be ER at R. This is flux. Flux will be energy per unit area. So we need to multiply by the area. The area is supposed to be perpendicular to the flux. And the area, in this case, is supposed to be area of the ring inside here. And that can be calculated from the circumference of inner circles multiplied by the thickness of this shell, which is delta Z. Okay? So the surface area that we need to multiply with the combined flux ER here is supposed to be circumference of inner circles 2 pi r multiplied by delta Z, which is the height of the shell itself. Okay? For the output, it would be exactly the same, except the location would be moved to R plus delta R, and the surface area, or the area here, would be the area of the outer circumference of the shell. So in this case, that would be 2 pi R plus delta R times delta Z. And of course, this has been done so many times already. I said, in this case, we need to change into 2 pi delta Z and bring this and this together into R ER at R plus delta R. This trick has been shown to you before. And without doing this, the differentiation would be totally different and would be very difficult. So in the same manner, for the input, you end up with 2 pi delta Z R ER at R. You can see that once we change these two terms to be the same form, then we can subtract them together divided by delta R, and then the limit of this term would give you the differentiation. All right? This is one direction of the red flux, the flux in R direction. Of course, there will be the flux for the blue fluxes in the axial direction. So in axial direction, the shell is supposed to be considered at the top and bottom part of the shell. And input, that would be the combined flux in z direction EZ. And it takes place at any z multiplied by the area. In this case, the area is supposed to be highlight area by blue color here. Of course, you can calculate by outer circle subtracted by inner circle, but that would be very, very complicated. Instead, if you can imagine that the thickness delta R here is very, very small, you can cut it and somehow expand this one into the rectangle. So if I do so, I will basically use inner circumference 2 pi r, which is inner circumference of the circle, times the thickness of the circle itself, delta r. Okay? For the output, it will be exactly the same, just changing location into z plus delta z, 2 pi r delta r. All right? So we have considered in and out fluxes for all sides already. So the rest of the term would be in the term relating to external work or work by external force. So the last term would be rate of work by gravity. If you recall, I told you that this term would be related to gravity only. Okay? So this work, the gravity force is basically the weight of the fluid within the shell. So basically you need volume of the shell multiplied by density. The volume of the shell is the area highlighted in blue, which is 2 pi r delta r, multiplied by the thickness delta z, that would be the total volume of the shell. If you multiply by rho, that would give you mass of fluid within the shell, times g, you change into the weight, into force already. And the work is basically force multiplied by the velocity. So velocity related to that direction, z direction, or the direction of gravity would be vz. All right? So we have all terms laid out for us. Let us put them together. So for the first two terms, you have 2 pi delta z r er at r subtracted by r er at r plus delta r. The second pair is basically 2 pi r delta r Ez at z minus Ez at z plus delta z. Okay, so this is in minus out for both directions, and then added by the work by gravity, which is rho 2 pi r delta z GVZ equal to 0. That would be our shear balance. So if we divide the whole equation by 2 pi, of course 2 pi will be cancelled. And then we need to eliminate delta z here. So we want delta r to be denominator here, and we want delta z to be denominator there. So we have to divide the whole equation by delta r delta z. If I divide it like that, delta z here would be gone. And then what we have here would be RER at R minus RER at R plus delta R divided by delta R. That would be the first term. For the second term, that would be EZ at Z minus EZ at Z plus delta Z divided by delta Z. Remember, we divide the whole equation by delta R delta Z. So this delta R will be gone, and we have delta Z as the denominator. Oh, we also need R here from this R. And then this term, if we divide by delta R, delta Z, we only have rho R G VZ left. So plus rho G R VZ equal to 0. All right? So when you see this form, you can take limit delta R approaching 0, delta Z approaching 0 at the same times. That means the shell is very, very small, very, very thin. So in that case, the first term turns to be differentiation minus of R ER with respect to R. Second term would turn to be minus EZ with respect to Z. And I move R in front here. Okay? And then plus rho GR VZ equal to 0. That would be our differential equation. But you can see that now it is a little bit complicated because this is not ordinary differentiation. It is partial differentiation. Because right now in this problem, temperature would be a function of two directions. So to sort things up a little, I'm going to divide the whole equation by R. That will be my equation 1. That will be used later. Of course, this is combined flux ER, and this is combined flux EZ. We need to expand them. By definition, combined flux ER is basically conduction flux plus convective flux in R component. Remember, the whole thing within parentheses is scalar. The R component of this flux is only VR. And then the flow work, that would be everything tau with the first subscript to be R times velocity in all directions added together. Okay? In the same manner, for Z component of the combined flux, we have exactly the same, just change the subscript from R into Z. So basically, if you plug these two equations into equation 1 and solve, that is your answer. That's done. But you can see that it is not quite straightforward. It's a little bit difficult. For each term, for instance, QR will be a conductive flux in R direction. It can be converted into temperature by using Fourier law. QR will be minus K dt by dr. Of course, you have to realize I use partial differentiation because now temperature is function of R and Z. Okay? For the second term, I don't care about whatever inside the parentheses because VR at this point is 0. Remember, from momentum transport, we have VR equal to 0 if I want to put it here. VR is 0, V zeta is 0, Vz is function of R only. That's from momentum part. So this VR will be 0 as well as this VR and V zeta. For Vz is not 0. What about tau Rz? This tau Rz can be calculated using Newton's law. Tau Rz, according to Newton's law, will be minus mu dVr by dz plus dVz by dr. Of course, dVr, the Vr itself is 0. And it is 0 everywhere, so this term will be dropped. So at the end, we will get two terms for ER. All right? For EZ, same thing for conductive flux, we will use Fourier law, QZ equal to minus K dt by dZ. VZ, this term is not 0, so we have to keep it. And we are here 0, VZ is 0. Tau ZZ, according to Newton's law, that would be minus mu 2 times dVz by dZ plus 2/3 of mu minus K times del dot V. For this term, we know for incompressible fluid like liquid, this would be 0 according to equation of continuity or mass balance. So we don't have to worry about this term. For the next term, this dVz by dZ is 0 because Vz is function of R, is not function of Z. That makes this term dropped. All right. Now, before plugging these two into the first equation or the equation here and solve for temperature, we need something else. The problem in this second part of the flux is enthalpy. Okay? First part, there's no problem. Temperature is measurable. Velocity is measurable. Both of them are what we want. The second part here, we have temperature, that's fine. We have velocity, that's also fine. Oh, this velocity, that's also fine. But enthalpy, this term is a little bit abstract. We cannot measure enthalpy. But according to thermodynamics, we can change enthalpy into the function of temperature. So we will do that first before plug everything back into the differential equation. So according to thermodynamics, we know that change in enthalpy, if you said enthalpy would be a function of temperature and pressure, and take differentiation, you can expand this enthalpy dH into two terms. The first term can be converted into Cp dt. I'm not going into the detail of thermodynamics, but basically you can split into two terms. The first term is function of temperature. The second term will be a function of pressure. The second term, you end up with this part. If you're interested in this term or you're not sure how to get this, basically it's involved Maxwell equation in thermodynamics. Now, if I integrate the left-hand side, I integrate it from, I have to integrate from one state to another. Okay? According to thermodynamics, the first state that can start, the initial state, is usually the reference state. So if I integrate from our reference state, and the reference state can be anywhere, doesn't have to be 0 degree or room temperature, it can be anywhere. I can choose reference state to be inlet of the pipe. I integrate from reference to any point in the system. So that means dH, once you integrate it, you get two H's, subtract each other. If I call H0 to be enthalpy at the reference state, I can get this part from the integration of the left-hand side. The first term, if you integrate it, let's say you integrate it from H0 to H. On the left-hand side, you integrate the first term from T0, which is reference state temperature, to any given T within the system. And this term, you integrate from reference pressure to any pressure within the system. Right? If I take Cp to be constant, of course, this is not thermodynamics class. Let's make this thing a little bit simple. If I consider Cp, or heat capacity, to be constant, you can get Cp times T minus T0. What about this term? For pressure, we know that for incompressible fluid, incompressible means the density does not change with anything. And density is basically inverse of the specific volume. So this is directly related to density. Basically, density is 1 over V prime, or V hat is 1 over rho. So it doesn't matter whether you change the temperature, density of incompressible fluid does not change. So in this case, the whole term is supposed to be 0 for incompressible fluid. So I only have this term left. This term, if I integrate from P0 to P of V dP, and I know that V itself is 1 over rho, okay? And rho is constant according to incompressible fluid assumption. Our liquid does not have density as a function of pressure. So you can take density outside of integration. What you have left is integration of dP. So what we have would be 1 over rho P minus P0. Okay? So that can be replaced into this equation to get EZ. So if I rewrite this a little bit, you get EZ equal to minus K dt by dz plus kinetic energy. Let me plug this velocity in each term separately. Okay, the first term would be kinetic energy. The second term, I have rho here, and H, according to what we derive from thermodynamics. Oh, by the way, this enthalpy at the reference point can be taken to be any number because enthalpy is relative, it's not absolute. So I can take enthalpy at the reference point to be 0 for simplicity of the problems. So let's say that at reference point, and we will take reference point to be inlet of the flow. So at this point, temperature is T0, which is the same as reference point temperature. And we can state that at this given temperature, enthalpy is 0. Okay? So if this is 0, we can drop this and take the enthalpy for the whole term on the right-hand side into this flux. So this flux starts with rho Cp delta T times Vz and rho times 1 over rho. 1 over rho is from here, delta P. And Vz. The rest of the term will be 0 already. All right? Now, a little bit further, this term, velocity, according to original equation, this is total kinetic energy. So velocity here is supposed to be the magnitude of your velocity vector. Of course, velocity can be calculated from velocity square equal to VR square plus VC zeta square plus VZ square. Okay, this is magnitude of each vector. And in this case, VR is 0, VZ is 0. So therefore, the net vector V is essentially VZ. So we can replace this velocity as VZ. All right? Now, let us move everything within equation 1 and rearrange. First term, minus 1 over r, d by dr, of r er. If I take r multiplied by er, I end up with minus r k dt by dr from the first term here. The second term is dropped because VR is 0. I only have this term left. So the second term would be minus come from here. This is minus. Oh, I'm sorry. This minus here. 1 over r d by dr and minus r mu. I have mu here. R from here, VZ, VC from here, and dVZ by dr. So basically, these two terms are from ER. Okay? Then, the second term, EZ, let me write down on the other line, minus d by dz. Now you see that for EZ, it is really, really long and really complicated. If I plug the whole thing here, it would make everything very, very hard. So I'm going to make assumption in this case. Let us consider this term comparing to the rest. Comparing to the rest here. Okay? By physical meanings, the first term is basically conduction. This is conduction in z direction. The rest is convection in z direction. We do not have flow work here. All flow works are gone. Okay? So we have conduction and convection in z direction. If you compare, if you look at the picture, you see that convection in z direction and conduction in z direction, which one is more important? Of course, if the entering liquid is hot, outlet liquid is cooler or cold, temperature will be dropped because the heat will be released from the pipe. Okay? If you look at conduction, it goes in this direction. If you look for convection, it goes in the same direction. They're competing, not competing, they're supporting each other. Okay? But we learned already in unit operation 3 that whenever we have convection and conduction at the same direction, convection is more important actually. You can think of this for another problem. If I have the pipe, the same pipe, but water entering this is cold and I heat it up, heat the pipe up. Okay? Cold water entering the pipe, heat the pipe, so therefore water going out of the pipe would be hot. Okay? If you look like this, in Z direction, there'll be conduction from high temperature to low temperature. So in this case, conduction should go from bottom up, while convection is going down. These two are competing. Which ones win? Of course, you say that convection will win in this case, especially if the flow rate is really, really high. Okay, so in this red problem, you will have conduction in R, convection in Z. Okay, and convection will win. If convection wins, in that case, we can say that the first term for the conduction can be neglected. For simplicity of the equation, we will neglect the whole term here. So the temperature will be a function of R only, and we can drop this for the moment. Okay? So therefore, EZ that will be plugged into the equation 1 will be convection only. The first term would be d by dz of 1 over 2 rho Vz cubed. It's cubed because we have Vz squared plus add by another Vz. Okay? If I have the whole term within the brackets, the other term would be differentiation with respect to z of rho Cp T minus T0 times Vz. Then d by dz. These two rows canceling each other, so we only have P minus P0 Vz. Right? So this is second term of this first equation. So this one is done, this term is done. Then we have another term left, the work term, external force, rho gr Vz equal to 0. All right? And you can imagine that this is really, really long equation. Even though I have two boards, I can expand them to cover these two boards. So let's eliminate some complication. First of all, this term can be easily removed. This term. Why? If you look closely, now density is constant for liquid. Liquid is incompressible fluid. I can take density out. Okay? I can take half out. What I have left in here would be basically differentiation of Vz cubed. And we learned from the very beginning that Vz is function of R. It's not function of Z. So differentiation here will become 0. Okay? So this term can be dropped. All right? Now the rest have to be sorted out nicely. So let us start. The first term, let me divide this, okay? Let's start with the first term. Plus, minus, you get plus. K is constant, take it out. So I have K inside 1 over R d by dr of R dt by dr. That's the first term. Okay? For the second term, mu can be taken out. Minus here, minus there, you get plus. Okay? So I have mu over R. Inside, you have to, I'm going to take this R and this differentiation term, add them together. So I'm going to get Vz multiplied by the red term. Okay? And that would be differentiation of a product. Like d of the uv equal to u dv plus v du. Okay? In this case, I'm going to get u equal to r times dvz by dr, and v would equal to vz itself. All right? So if I consider the whole term here to be a product of two terms, red term and vz, and take this as a differentiation of the product using this simple calculus, you can expand them into two terms. So the first term is u dv, and my u is r dvz by dr. So that's r dvz by dr. That's the first term, that's u. dv would be dvz by dr. That's the first term from the expansion of differentiation of the product. The second term would be v du. V itself is vz. du, d would be d by dr of u, which is the whole thing here. All right? That would be our second term in this lengthy equation. The third term is already dropped. The fourth term. Now you should see that Vc here, actually everything is under differentiation with respect to z. And Vz is a function of r, it's not function of z. So you can take this Vz out. Of course, density and heat capacity will be considered constant, take it out. So what I have would be differentiation. Oh, I have minus over here. Okay, so minus rho Cp Vc that was taken out. What I have left would be differentiation of T minus T0. The first term would be dt by dz. The second term is differentiation of T0, which is reference temperature. You can take reference temperature to be inlet temperature, but anyway, it is constant. It does not change. The inlet temperature does not change with the length, right? It is called inlet temperature. So therefore, it's fixed at the inlet. So this differentiation would be 0. I have only one term left. Then, same thing for this term. Vz is not function of z. You can take it out. You can take differentiation inside this parenthesis. You get differentiation of pressure and differentiation of reference pressure, which is constant. So the last term would be minus Vz dP by dz. And then the fourth term, rho grVz. That equal to 0. All right. So let me rearrange the equation a little bit. So I'm going to move this term to the right-hand side and write it down first. So let me have rho Cp Vz dt by dz equal to, remember I put this term to the right-hand side. The rest stay on the left, okay? First term on the left would be this term, would be K over R d by dr of R dt by dr. Second term, now I can multiply this mu over R to this term and to that term. For the first term, you see that these two R's cancel out. What we have would be mu. And this term, these two terms are basically multiplying each other. So I will end up with dvz by dr squared. Okay? Then the next three terms, I have Vz, Vz, Vz as a common term. So if I take Vz out, inside, let me write down this pressure term first. I have dP by dz. And then this term, taking this mu and R inside, I have mu over R d by dr R dvz by dr. Okay? And the last term, oh, I'm sorry. This term was already taken care of. This must be incorporated. These three terms combined. So the last term will be this term. Oh, this term R should be gone. From what I erased already, there's a 1 over R. So this term, there is no R here. From the very beginning, because I divide the whole equation by R, so this term should be gone, I'm sorry. So there's no R in this term. So this should have rho G. There. All right. Now, if you look at the equation, this represents convective transport in z direction. Okay, it has velocity, it has heat capacity. Physical meanings of heat capacity is ability of fluid or substance to carry energy. So it carries energy by flow. So this is convective transport in z direction. This term, you have thermoconductivity, so it is related to conduction. It has conduction in R direction, so this is conduction in R. This, what about this term? It has velocity, it has viscosity. So this is what we discussed earlier. This is viscous heat term. It is basically transformation from flow work to internal energy. The higher the flow, the higher the viscosity, the higher the chance of transform into internal energy or higher in temperature, just like meteorite entering atmosphere. So as long as the flow is not extremely fast or the viscosity is not extremely high, this term can be dropped. Okay, so in this case, in our examples, we will drop this under assumption that viscous heat is negligible. What about this term? All these complicated terms. Basically, if you look at another equation, Navier-Stokes equation. Okay? Let us set up Navier-Stokes equation in z direction. And you are wondering why. I will show you in a minute. So let me write the equation first. This is Navier-Stokes equation for z direction. The equation is rather lengthy. All right. So this is Navier-Stokes equation. You can look it up from appendix in the textbook. Okay. So if we are trying to handle this equation separately from the blue equation up here, the first term will be dropped by steady state assumption. Okay. VR is 0, Vz is 0, Vz is 0, but Vz is not function of z, so this differentiation will be 0. All right. Pressure still changing with respect to z. Okay, in flow in pipe, there's a pressure change with respect to the length of the pipe. Vz is function of r. This term must be kept. But Vz is not function of zeta. This term can be dropped. Vz is not function of z either. This term can be dropped. What do you see? Now you see this here. This term is there, and that term is there. All right? So this term, and that term combined is exactly the same as whatever we have in this bracket. And you see that if you take the rest to the left-hand side, you end up with the whole term here being 0. Okay? It will be canceled out by means of Navier-Stokes equation. So basically, what we have left for this sample is only 2 terms. Okay? So only 2 terms left. But these 2 terms is tough enough for you to integrate. So let me write down again. Rho Cp Vz dt by dz equal to k over r d by dr r dt by dr. What does it mean? As I said, this is convection in z direction This would be conduction in our direction. So if you look at the picture of your system again, right now you have heating or cooling of the water. Let's say you have cooling, hot water entering, cold water going out. It means that convection, whatever is flowed through this pipe, the energy being carried by the flow here, going down here, is essentially going out in this R direction so that liquid leaving the pipe is cooled down. So if you look in terms of energy balance, energy going in equal to energy going out. It's going in by means of convection, it's going out by means of conduction. So that's energy balance. Okay, so we end up with this simple energy balance that has physical meanings as well. In order to solve this equation, I'm not going to ask you how to integrate this one. It's rather complicated because this is partial differentiation. You have temperature as a function of R and Z. But just make it a little bit more complicated. You will see that Vc is now Vmax 1 minus R over R squared. So this is a function of R as well. So in order to make integration, to do the integration, you need to move this to the right-hand side. And therefore, this R squared, which is in the brackets here, would appear as denominator, would be very, very complicated. But what I want you to be able to identify is not how to integrate this one, but how to identify boundary condition necessary for the integration. Okay? If we count, on the left-hand side, you have first-order integration with respect to z. That means we need one boundary condition with respect to c. On the right-hand side, you have second-order differentiation with respect to r. That means you need two boundary conditions with respect to r. What do we know? One boundary condition with respect to z, we know that entering temperature is one value. So that means at z equal to 0, any r. Right now we have temperature as function of two variables. When you state the boundary condition, you have to state both. This one is z equal to 0, any r. Temperature is T0, or one value. And remember, we take this reference temperature as an inlet temperature. For two boundaries with respect to R, of course, we know at the wall, at R equal to capital R, this is at the wall, you may have anything that we know. For instance, there might be heating or cooling with constant temperature at the wall. Let's say you have hot water entering the pipe, and the pipe itself stay at the room temperature, atmospheric temperature, so wall temperature remains constant. On the other hand, you may also have constant heat flux. That means the flux leaving this pipe would be constant at all time or at any length. That depends on the problems. In this particular problem, it states that the flux will be constant at all distance. So in this case, at R equal to capital R, any Z, QR is constant. It's constant flux leaving the pipe. And this QR can be represented by Fourier law minus K dt by dr equal to constant. Okay? This is the first boundary with respect to R. The second boundary should be at the center. We have done the problem with the pipe for several times already. The other boundary will be at the center. And we know that temperature profile in this picture, whether if this one is cooling, you can plot temperature. And this is R, this is temperature, okay? It's going hot here, cold down here. So therefore, the wall itself should have low temperature than the inner. So temperature is supposed to go down low at capital R. And at R equal to 0, temperature is supposed to be highest. And of course, because the pipe itself is symmetry, it should have some inflection point over here. So that would be our boundary. So at R equal to 0, any Z, you will end up with dt by dr equal to 0. That represents slope of this line. You may also state that T at center is finite, and hopefully it can be solved using the mathematical form. Either way, you can state the boundary condition. Okay? From this to the solution, it requires lengthy math, so I'm not going to cover that part. The rest of this chapter 10 is, I think, we cover all the chapter 10s already. So let us summarize whatever content in chapter 10. Chapter 10 is basically the energy balance using shell balance and its collection of examples. We start with conduction, example with conduction only. Remember the conduction in the pipe, in the wire. But the first examples, I show you how to incorporate the non-mechanical work, electricity, for example. Second example is still conduction using composite wall. Remember, we have several walls connected together and heat is transferred from one side of the wall to another. But in that case, we also incorporate convection in somehow, but convert the form of convection using Newton's law of cooling so that convection can be represented by using conduction equation. So still the first and second examples relies on equation based on conduction. The third example is basically the flow in slit with viscous heat. That example shows how important the viscous heat of flow work would be. If the flow work is high enough, you can have increase in temperature within the system. Okay? The fourth example is in viscous heat, we have the momentum. Viscous heat example is the first example that have momentum and energy transport at the same time. We allow fluid to flow. Okay, but in that particular example, convection is not as important as the flow work. So we drop convection term, we use flow work and calculate the temperature profile. The fourth example is natural convection. In that case, we still have both energy transport and momentum transport, okay? But in that case, we have to deal with energy balance first because density is a function of temperature, all right? And then comes with these examples, forced convection. The problem must deal with momentum first because convection is more important and we need velocity profile to calculate convection part. And that will be the rest. All right? So that's it for chapter 10. Next time we will move on to chapter 11. The concept of chapter 11 will be in the same sense of mass balance or momentum balance. We just want to generalize this shell energy balance into equation that can be used for any particular problems. All right? So see you on Thursday.